Okay, so we're going to look at energy, work, and power, and this is a bit of a longer lesson, so if you want to break it up into each of its kind of subsections, please do. Okay, everything in the universe is a manifestation or form of energy. So energy is fundamental to everything. All physical processes can be understood by the transformation of one type of energy into another. Okay. So chemical energy exists within the bonds of atoms held together. Radiant energy is like light energy, but it can also include heat energy. Electromagnetic is electrical energy. Atomic is energy within the nucleus of an atom. And mechanical energy is kinetic energy, which is motion, gravitational potential, which is due to a gravitational field or being at a height of something, and elastic potential energy, which we talk a lot more about in our next unit. What you do need for this topic is just this formula. So in Physics 30, they work with all the other types of energy, but right now we are only going to work with mechanical energy. So this section is what's really pertinent to us right now. Okay, so of mechanical energy, there's two basic kinds. There's kinetic energy, so due to motion. And then there's potential energy, where something is stored, has stored energy. So there's many different types of potential energy, and we just focus on gravitational potential and elastic potential. Okay, the idea of energy and work came from the discovery and invention of the steam energy, and then they were really involved in it in the Industrial Revolution, when there was like factories and they wanted to increase the output. Okay, laws of energy. This is where we need to really start. So the total is neither increased nor decreased by any process. So we cannot create energy. Energy can only be transformed from one form to another and transferred from one object to another, but the total amount of energy remains constant. Again, we cannot create energy. Heat flows naturally from a hot object to a cold object. Heat will not flow spontaneously from a cold object to a hot object. A consequence of this one-way flow is that no device is possible which can completely transform a given amount of heat energy into work. Some mechanical energy is always lost as heat. So if we are using heat energy to do anything, that process will not be able to absorb all of that heat because the mechanics involved actually absorb some of the heat. Plus, it's impossible to transfer all heat. At some point, things will reach a heat equilibrium and no more can be transferred. All right, so work has a few different meanings, but what we're going to look at is the primary definition here in physics. So work is done on an object if its mechanical energy, so kinetic or potential, changes. All right, so this is a big idea. Work is equal to the change in energy. So if I lift an object up, I have transferred potential energy. So I have given it potential energy by lifting it and putting it on a shelf where it could potentially fall. Work is done by applying a force through a distance. Okay, so work is done by applying that. Excellent. Okay. So if there's an angle between the force and the distance, this equation becomes W equals force cosine times the change in distance. Now, what you can remember is if we are moving an object over some distance, we need to use the force in that direction as well. So because this force is at an angle, I need to calculate it back to its components. I'm going to find the force in the x direction. To find the force in the x direction, that will be cos theta times the hypotenuse. So that's where they've gotten this formula from. I just remember to calculate f of x and then work from there. So again, the force and the displacement have to be in the exact same direction. All right, work is a scalar quantity with units of Newton meters or joules. So we don't need to consider its direction. Note when theta equals 0, the force is parallel. So if I do not have an angle here, the force will be as listed. If my force is at 90 degrees, so opposite, the x component of this force would be 0. So if I drew this, if that's our force, there is no f of x. Therefore, the force in the x direction is 0. And if that's the case, work is 0. No work is done. All right. So a workman exerts a horizontal force of 30 newtons to push a 12 kilogram table 4 meters across a level floor at a constant speed. Calculate the work done. So work is equal to force times the distance covered. Work is equal to the 30 newtons applied times the 4 meters it was pushed. There is no need for the mass in this question. So we get 120 newtons, which technically I should put to 1.2 times 10, Newton meters, times 10 to the 2. And a Newton meter, again, can be considered a joule. Okay, so either unit, doesn't matter. All right, find the work done in pulling a luggage carrier by 45 newtons at an angle of 50 degrees for a distance of 75 meters. So we have an angle here. Our force applied was 45 newtons. And again, that is at an angle of 50 degrees. I need to find f of x. So f of x is 45 newtons times cos of 50, which is 28.93 newtons. Now, again, we can use the distance covered with that same force. So work is equal to force times distance, 28.93 newtons times our 75 meters equals 2169 Newton meters, which is 2.17 times 10 to the 3 Newton meters. Okay, so again, because this was a horizontal distance, we need the horizontal component. You can use the work is equal to cos theta times F times D, or you can just solve for your components. Work is defined as a change in mechanical, so that's kinetic or potential energy. So work can be positive or negative depending on the direction that force acts. So we have example 3 here below to show that. So a weightlifter is bench pressing a barbell whose mass is 110 kilograms. He raises the barbell a distance of 0.65 meters above his chest and then lowers the barbell the same distance. The weight is raised and lowered at a constant velocity. Determine the work done on the barbell when the barbell is lifted. So in A, our change in distance is positive. We are moving upwards by 0.65 meters. So we need to use the idea that work is equal to the change in energy. And because we are looking at a change in height, we should be looking at potential energy here. So the potential energy is mgh, which was our 110 kilograms times gravity. And we're going to use the positive value here, times our height of 0.65 meters. So this is the potential energy at the top. We end up with a potential energy of 701.415 joules. Now, if you want to prove this to yourself, we need the potential energy at the bottom. So that would be mgh, where h was 0. So we get 0. Work is equal to the change in potential energy, which is the final position. So the top, so 701.415 joules at the top. Take away the bottom, so 0 joules at the bottom. So work is 7.0 times 10 to the 2 joules, just two significant digits. For B, when it's lowered, we're just going to do the opposite. So work is still equal to the change in potential energy. So when it's lowered, it starts at the top and ends at the bottom. So our energy at the bottom is 0 joules. Take away the energy at the top, and we get negative 7.0 times 10 to the 2 joules. All right, and C, the net work done when it goes up and comes down. So work is equal to the change in potential energy. Well, where it started and where it ended is 0 joules. So 0 joules at the end, take away 0 joules at the beginning is 0 joules total. And don't forget, a joule is equal to a Newton meter, so you can use those interchangeably. All right, 50 kilogram crate is being dragged across a floor by a force of 200 newtons at an angle of 40 degrees from the horizontal. The crate is dragged a distance of 5 meters and the frictional force is 60 newtons. So what is the work done by the crate by the applied force? So we need to calculate the force of X. Again, that'll be 200 times the cos of 40, which I got to be 153.2 newtons. So work is the force times the distance covered. So the force in this case was our 153.2 newtons times the distance covered, which was 5 meters, and we get 766 Newton meters, or 766 joules, doesn't matter. Technically, I guess this should be 7.7 times 10 to the 2 Newton meters with significant digits. What is the work being done on the crate by the frictional force? Well, the frictional force is still in the same plane, so work is equal to force times distance. We get the frictional force was 60 newtons in the same plane, so we don't have to do any component work, and 5.0 meters. So we get 300 Newton meters, or 300 joules. Again, I should probably put this into significant digits, so 3.0 times 10 to the 2 Newton meters. What is the net work done on the crate? So work is the applied plus the frictional, considering their signs. So the applied force, I'm going to use its unrounded value, was 766 Newton meters. Take away the frictional work, so take away 300 Newton meters, and we get 466 Newton meters. Again, this one's negative because it's in opposition of our direction. What forms of energy were produced by the net force and the applied force? Well, the net force, we ended up having kinetic energy. We were moving. The applied force, as we were applying these forces, we had kinetic in this direction, but we also created heat energy because of the friction in this direction. Okay, so these are just derivations of our equations. You do not need to know how to replicate these, so I would kind of get rid of those. Something to note here, though, at the end, elastic potential energy. So if we have a spring and it's stretched across a distance, we know that it gets harder and harder to stretch that spring the further it's pulled out. So that's what they're saying here, that the force is increasing as the distance increases. So they say, if we looked at this, this line would be, the slope would be K. So if we looked at the equation of this line, Fy is equal to mx, and where m is k, and k represents the spring constant. So some springs are really easy to stretch and some are really hard to stretch, and that's because they have different spring constants. So what we're going to use in this unit a little bit is that force is equal to K times X. And this formula, this one's on your formula sheet. All right, a 20 kilogram object is lifted from a table to a vertical height of 0.5 meters above the table. What is the gravitational potential energy of the object with respect to the table? So we're looking for EP, which is mgh. We have a mass, we have gravity, and the distance lifted. Multiplying all of those together, we get 98 joules. All right, an archer draws back an arrow by exerting an average force of 90 newtons on the string. So we're given a force of 90 newtons. If the string is drawn back 80 centimeters, so we have a distance. What is the elastic potential energy of the string? So we're looking for EP in this case. Now we don't have enough energy information, If we wanted to use 1/2 kx squared, we have x squared, we have how far back it was stretched, but we don't have the elastic potential constant for it, so k. Therefore, we can't use this formula. But what we do know is that work is equal to the change in energy, and work is equal to force times distance applied. So this change in elastic potential energy could be calculated with our 90 newtons and our 0.80 meters of stretch. So we can get 72 joules just using this formula. All right, a 50 Newton force stretches a spring by 0.75 meters. What is the spring constant and how much energy is stored in the spring? So we are given a force and we're given a distance or x. So this is where we're going to use our F is equal to K times X formula. So we have force, we have distance or X, so we can find our spring constant K. So K is equal to 50 newtons divided by 0.75 meters, and I get that K is equal to 75 newtons per meter. So we can now use that in our EP equals 1/2 kx squared. I have K, I have how far the spring was stretched, I can calculate the potential energy. So 1/2 67 newtons per meter times x squared, 0.75 meters squared. And we get 18.84 joules or 19 joules rounded. This won't come up a lot here, just like this once or twice. So don't fret too much if you're like, I am unsure of springs. I won't put them on your assessment coming up. I'll wait till we have actually covered springs. Okay, what is the kinetic energy of a 40 kilogram object that's traveling at 50 meters per second? This is a little bit of a grade 10 review question. So we have the mass and we have its velocity. And we're looking for EK. EK is equal to 1/2 mv squared. So 1/2 40 kilograms times 50 meters per second squared. And we end up with a giant number, 50,000 joules, which you can either write as 5.0 times 10 to the 4 joules, or you can turn it into kilojoules. So 50 kilojoules is also acceptable. Last page. The rate at which work is done, or the rate of energy consumption, is called power. So a useful alternate formula, which is not on your formula sheet for power, is that we start with power is equal to work over time. And we know that work is equal to force times distance. So we inputted force times distance here. Now, if you separate this, power is equal to force times distance over time. I know that distance over time is equal to the average velocity that something is traveling. So if I sub these out, I can get that P is equal to force times velocity, which is what they have here. Okay, how much work can a 1.5 kilowatt kettle do in 10 minutes? So power is equal to work over time. The unit for power is watts. All right, to solve for work is equal to power times time. So work is equal in this case to our 1.5 times 10 to the 3 watts. Again, to get rid of 1.5 kilowatts. A kilowatt is equal to 1,000 watts. So we get 1,500 watts. All right, so that's where I got the 1.5 times 10 to the 3. And we need to multiply by time. Time needs to be in seconds. So 10 minutes is equal to 600 seconds. So we end up with a giant number, 900,000 joules, which is 9.0 times 10 to the 5 joules, or 0.90 megajoules. Whatever unit you would like to use is fine. A car driven at 100 kilometers per hour is overcoming a frictional force of 3,200 newtons. How much power is being produced, and what is the horsepower? Okay, I like the first part of this question. Horsepower is kind of out of our curriculum and study, but I'll do it anyways. Okay, first things first, we need to change 100 kilometers per hour into meters per second. So in 1 kilometer, there's 1,000 meters, and in 1 hour, there's 3,600 seconds, and I get 27.78 meters per second. I know that it's ridiculous that I still do my unit conversion like this, but I know that I'm getting the question right, and I don't have to think about whether I'm multiplying or dividing by 3.6. Okay, power we're going to use is equal to force times velocity. So this final formula up here. So the force of friction is 3,200 newtons. The velocity is 27.78 meters per second. So we get 8,889 watts, which is 8.89 times 10 to the 4 watts. Now, what you needed for this to finish the conversion is that 1 horsepower is equal to 745 watts. So if we take our original answer here, our 8.89 times 10 to the 4 watts, and I multiply to cancel watts and find horsepower, I put in that 1 horsepower, 745 watts, and I get 119 horsepower. So I'm not sure where 105 came from. I'd go with 119. All right, this is a big lesson, so please make sure that you go back and do a little bit of extra practice to be comfortable with this. Spring constants isn't something that I would focus as much of my energy on at this time. Again, we're going to double back on it, so please just focus on potential and kinetic energy, like gravitational potential, as well as work and power.